Hi, I'm John Donahue from the Institute for Quantum Computing at the University of Waterloo. Today we're going to be talking about quantum entanglement, a special correlation that can be shared by quantum objects like photons and electrons. Imagine you have a pair of shoes, a left shoe and a right shoe. Without looking, you take each shoe and put it in a different box and give one to your friend. Now let's say they get into a rocket ship and fly off to Mars. After they reach the Angared planet, you open your box and find that you have the right shoe. Now you know with certainty that your friend has the left shoe. These results are what we call correlated. Knowledge about one of the shoes gives you knowledge about the other one. Quantum correlations can go beyond shoes. I can have a pair of correlated electrons, where when I measure one to be magnetically pointing up, I'll measure the other to be magnetically pointing down. If instead I measure the first to be magnetically pointing down, I'll measure the second to be magnetically pointing up. This so far is exactly like our shoe example. But unlike classical particles, quantum states can be measured in many different ways. For example, instead of asking the electron if it's pointing up or down, I can ask it if it's magnetically pointing left or right. And if I measure one electron to be magnetically pointing to the right, I'll find the other electron to be magnetically pointing to the left. We call these kinds of quantum correlations entanglement. Even if we take one of those electrons on that rocket ship to Mars, we'll find that it's always magnetically pointing in the opposite direction of the other, even if we don't choose which way to measure them until they're already on different planets. Rather than thinking about them as two separate electrons, we have to consider them as being in a single joint entangled quantum state, even when they're separated by a very large distance. Researchers have shown that entanglement can persist among photons separated by many kilometers. We can also design experiments that prove entanglement using ideas from game theory, where players cannot win with classical correlations alone. Entanglement isn't magic. For example, entanglement cannot be used to communicate faster than the speed of light. However, it can be a very powerful resource for quantum information science and technology. Entangled networks of particles can be much more sensitive than individual quantum systems, allowing them to be used as delicate and precise quantum sensors. The ability to make these joint entangled quantum states greatly increases their complexity and is widely believed, though not proven, to be a key resource for quantum computing. To learn more, explore Quantum 101 at uwaterloo.ca/IQC.